All right, welcome back, guys. If you will take a look at my first official video, thank you for doing that. I hope you watch this one too, right? Just trying to build a channel currently. So all this may look like random stuff, but promise you, well, I'm not going to promise because I don't know if we're going to do that. But we're going to start working on a project, will be more beneficial, right? But today, what we're going to be doing is we're going to be proving that d by dx of sine of x is equal to cos of x. We're going to prove why it is equal to cos x, right? Right? And we're going to write some limits that we're going to be using over that side, as well as the trig identity that we're going to be using, so that when I make reference to it, you understand what I'm doing. All right? So we are going to recall that the limit as x tends to 0 of sine x over x is equal to 1. And we're also going to recall that the limit as x tends to 0 of cos of x minus 1 over x is equal to 0. Hope I got that one right. But I think it's right. Okay, and we're also going to use a trig identity, the trig identity for the double angle, I think, the sine of alpha plus beta is equal to sine of alpha cos of beta plus sine of beta cos of alpha, right? And we're also going to be using the definition of the derivative, and that's from first principles. So I'm going to write that here also, but I may erase it for space. So we're going to take the fact that the limit as h tends to 0 of f of x plus h minus f of x divided by h. This limit right here is the definition of the derivative. All of this is equal to f prime of x. We're going to write the derivative as that, f prime of x, all right, or the derivative of x. So if you did any pre-calculus class or calculus class, you would know the definition of the derivative right here, which we use. So that is what we're going to be used to prove this, because we all know that the derivative of sine x is cos x. But why is it cos x? That's what we're going to be proving here today. Okay, so I'm going to be using green, my favorite color. Now, if f of x, if f at x is equal to sine x, then f of x plus h is equal to sine of x plus h. See that? Because we're going to need f of x plus h, and we're going to need f of x to plug into the limit formula, right? So to find f, going back to purple, my favorite color, to find f prime of x, we are going to take the limit as h tends to 0 of sine of x plus h minus sine of x all over h. That's what we're going to be doing. Now, the first thing I'm going to do is to use the trig identity. That's right here. We're going to be using this one. Let's go use red. And we're going to use it to expand this out right here. So now it is customary to write the limit all the way. But what I'm going to do is sometimes I'm just going to ignore this for a bit until we get to the final answer. Not a good thing to do. If you're working on, like, for example, an exam question, then you follow through with the limit. I'll try my best to do it, but sometimes I forgot to just write it down because I'm so into what I'm working with. So don't judge me. Let's go. So we're going to expand this out. So the limit as h tends to 0 sine of x plus h is going to be, as you can see, x represents alpha right here, and h represents beta. So we're just going to replace where we see alpha with x and where we see beta with h. So this is going to be equal to sine of x cos of h plus sine of h cos of x. And we're going to subtract sine of x. Let's put those in parentheses like that. So it's starting to differentiate it. And we're dividing all of that by h. All right? So this is just a sine of x cos of h plus sine of h cos of x minus sine of x. All right? Now we're gonna move the sine x over here, because you can see this, the sine x is right here and sine x is also right here. So we can consider those to be like terms. All right? So we got a term in sine x over there and a term in sine x over here. So we can factor that out. So we're gonna move this sine x right here. Let's put that in green, favorite color. We're gonna move this sine x right here, and we're gonna move it closer to this so that you can see what's happening when I factor out the sine x from those two terms. All right, I'm gonna leave this over the other side because we're gonna be splitting up the fraction. All right, and I think I can erase this piece right here, because as gradually as I go, I'm gonna need the space. All right, so let's erase that piece right here and erase this piece right here because we have already used that. Right? So I'm going to continue down here. So down here we have the limit as h tends to 0 of, so I'm going to factor out a sine x, but I'm going to write it so that you can see what's happening. Sine of x cos h minus sine of x, and then we're going to add sine of h cos of x, all divided by h. There we go. So as you can see here, we have a sine x here and we have a sine x here. So I'm going to factor out a sine x. So the limit as h tends to 0, I'm going to factor out the sine x out here, sine of x, and in the parentheses, sine x times cos x gives me sine x cos h. So we're going to have a cos of h, and we're going to subtract sine x times what gives me sine x, which is 1. So we're going to put that 1 right there. And then over on this side, we're just going to have the plus sine of h cos of x. And that's all over h. Coming nicely. Now, what we're going to be doing here is we're going to be splitting this fraction up, right? We're going to split it up so we can take it apart and then put it back together, all right? We're going to be using those. It's coming nicely. As you can see, that the cos x minus 1 is already there, right, in that form. So we're going to be splitting this fraction right here. So remember, we can write this as a fraction of over h and a fraction of denominator h over that side also. So let's go using green again. So I'm going up here. So the limit as h tends to 0, we're splitting the fraction up. So we're going to have sine of x and in parentheses cos h minus 1 all over h, and we're adding that over that side. We're going to have sine h cos x all over h. See what I did there? I just split the fraction up, right? Because if we add these two, we get back to this right here, okay? And then I'm also going to do something right here. We're going to split this again because this is being multiplied. So it doesn't matter where I put the denominator here. I just need to ensure that it is being multiplied, right? So I'm going to split it so that it gets in this form right here. And I'm going to split this one over here so that it looks like this right here. So using purple again. So the limit as h tends to 0. So I'm going to split this fraction here. This is the same as And you know what? Before I split this up, what I'm going to do, I'm going to redefine the limit, because the limit of the sum is the sum of the limits, right? So I'm going to take the limit as sine x, right, times cos of h minus 1 over h. That's the same thing as what we have here. I just write that so I could get it in this form right here. And then we're adding that to the limit as h tends to 0 of sine h over h times cos x. So again, the limit of the sum is the sum of the limits. All right. If you don't recall that fact, you can go back and check on limits, and you should see that. Okay, so because the limit, I think the limit is a linear operator. That is why we can do that. Now over here, as you can see, the limit of the product is a product of the limit also, but instead of splitting this up, right, to save me some time and space, I'm going to highlight these two limits here in red. I'm going to highlight this in red and this in red right here. So as I say again, the limit of the product is the product of the limit. So I could split this up as the limit as h tends to 0 of sine x times the limit as h tends to 0 of cos of h minus 1 over h. But to save us some space right here, what I'm going to do is to show you that this limit right here, this limit is just equal to 0. So anything times 0 gives me 0. So all of this over on this side, using green, my favorite color, all of this on this side here just goes to 0. So it's actually 0 plus, let's go over here, 0 plus the limit as h tends to 0 of sine h over h times cos of x. Now, the limit as sine h over h, what is that limit equal to? If we recall over here, if you replace x here with h, then you'll see that it's in that form, it's still equal to 1. So here, in reality, we just have 1 times cos of x. Now, cos of x is not a function of h. So in reality, we just need to take the limit as h tends to 0 of sine of h over h and multiply that by cos of x. Because we could take cos of x outside the limit. We could rewrite this as, let me rewrite it for you. It's going to be cos of x, right, times the limit as h tends to 0 of sine h all over h. See that? Because cos of x is not a function of h. So we could take that outside the limit. So now, the limit as h tends to 0 of sine of h over h is just equal to 1. And we have in the final step of this right here, it's 0 plus cos of x times 1, which is still cos of x, but I'm going to put the times 1 right here, times 1. So that's 0 plus cos x times 1. That's just equal to cos of x. And that, my viewers, is how you prove that d by dx of sine of x is equal to cos of x. Thank you for watching. I'll see you in the next random video.